type of diagram that I want to go over, which is another way to visualize vapor-liquid equilibrium for a multi-component system, is a TXY plot. And the TXY plot relates the mole fractions in the vapor and the liquid phase for a multi-component system. In this case it's binary, so we have A and B. And it relates the mole fractions in the liquid and vapor phase to the temperature. And so here's the plot, a typical plot we might see. And the mole fraction, again, goes from 0 to 1 here, because that's the ranges that we can only ranges we can have for mole fraction. And in this case it's plotted for the more volatile component. And in our example we've been using, this has been A. And what it shows you here are several lines. Like here, I have a line here and a line here. Well, what do these lines represent right here? Well, these lines are representing the division between different phases of our multi or binary component system. And so what I have here is I have a region up here above this second line. This is the vapor region, or superheated vapor. And this is the gas phase region. Then we have here the liquid, or subcooled or supercooled liquid region. And then in this region, between the two lines, we have what's known as a mixture. And so this means that we have liquid and gas in equilibrium with each other. And so depending on our temperature and depending on our mole fraction, we may have a vapor, liquid, or we may have a mixture of the two. So for instance, if I am at a mole fraction right here and I'm at a temperature up here, that matches up somewhere around here, I have to have a vapor phase. So all of my particular compound is in the vapor phase. So we might not necessarily have something that's a mixture or a vapor and liquid in equilibrium, depending on our temperature where we're at. If we're at high temperature and we're at the concentrations in this region, then we may have only vapor phase. We may not have a liquid phase. On the same hand, if I'm at a low temperature and I'm in these mole fractions down here for my light component or more volatile component, I may be only liquid. But somewhere in between the two extremes, I will have a mixture or a vapor and a liquid equilibrium. Now, what do we call these lines right here? You may have guessed it. This is our saturated vapor line, and this is our saturated liquid line. So if we are on this line right here, we are a saturated vapor. If we're on this line right here, we are a saturated liquid. And just to remind you, a saturated vapor is a vapor that is only a vapor, no liquid present, but it's almost about ready to form a liquid. And the same thing here, a saturated liquid is just a pure liquid, but it's so close to forming some of the vapor, but it hasn't quite formed it yet. And that's the saturated liquid line right there. Let me just add one other thing, that this line right here, the x-axis is the mole fraction for both the liquid and the vapor. So it's like I said, it's an x and a y here. So when we are measuring or we are trying to find out what the mole fraction is in the liquid phase, we just find out where it is on the x-axis. Or when we're looking at the vapor phase, we can just look on it on the x-axis. So when we want to find x or y, we can get both of them from this x-axis here just by reading down whatever it is. So let's look a little bit more about how we utilize and read this diagram as it pertains to mixtures. So let me just start out with an example compound. Let's just say I am somewhere about right here. So that's maybe a mole fraction of about 0.5 for component A. So that means that the mole fraction for component B is about 0.5, just to add up to 1. And let's just assume that we are at this point right here, this x. Well, this is in the liquid region, so we are a pure liquid, and we have no vapor present, and our mole fraction for A and B are about 0.5 each, and they both add up to 1. Let's just say we raise the temperature on this. Well, what's going to happen as we raise the temperature of this mixture? Well, eventually we're going to raise, and we're eventually going to hit the saturated liquid line. So at that point we have a saturated liquid right here. And as we raise the temperature higher and higher, we are in this mixture region. So we have a mixture of liquid and vapor were in this region where we're raising the temperature. And eventually what will happen is we will raise the temperature higher and higher until we get to the saturated vapor line. And then as we raise the temperature even higher, we'll get in it here to the get into the superheated vapor line. And so it's a function of the temperature where we are at on this curve. Now, how do we deal with this mixture region right here? What do we know what's going on here? Well, I know the mole fraction in for the component A and B can be found in the liquid phase just by reading down here. The same here in the vapor phase. I can just find out where I'm at, the temperature, and then read down here and I get the mole fraction of the vapor phase. But when I have a mixture, it's not so quite as easy to find out what the mole fractions in the liquid and the vapor phase are. And the way that you do that is at a given temperature, you read across to the left and the right to find out what the concentrations or the mole fractions are. So let's just put a little X there. Let's just assume that we are a mixture of A and B, and we started out as a liquid down here, and then we heated up to this particular temperature that we read across here, and we're at this point on the TXY plot. Well, to get the mole fraction of the vapor, what we do is we read over here across. So let me just put a little mark there. And to find out what the mole fraction is in the vapor phase, or excuse me, the liquid phase, we read over here across. And so these points on the saturated vapor and the saturated liquid lines, these are the lines, these points on these lines, these tell us the concentrations in the vapor and the liquid phase. So this tells us what the concentration or the mole fraction of A is in the vapor phase. This tells us the mole fraction of A in the liquid phase. The overall concentration, if you were to take the vapor and liquid all combined, would be this mole fraction of A, but the actual individual components for the two phases are on the saturated liquid and the saturated vapor line. And again, if I'm at another temperature, say I'm at this temperature, again I would read over here to the saturated liquid to get the mole fraction in the liquid, and I'd read over here to the saturated vapor line to get the mole fraction in the vapor. So depending on the temperature, the mole fractions in the liquid and in the vapor are changing and are different. So it very much depends on the temperature of my mixture that I am that determines what the mole fractions of the vapor and liquid line are. One other thing that I want to mention is the lever rule. And the lever rule is just a simple rule that tells us the relative amounts of vapor and liquid. So this plot, if we just look at it, look at the x-axis here and the temperature, it will tell us the concentrations or mole fractions. It will tell us the mole fractions in the vapor and liquid phases, but it won't tell us how much vapor and how much liquid we have. We may start with this initial amount of liquid down here at say 100 moles, but as we heat it up, some of that is going to vaporize or become a gas, and we don't know how much. Could half of it vaporize? Could 1/3 of it vaporize? How much? Eventually, as we heat up, all of it will vaporize, and when we're in the gas phase or vapor region, everything that we initially start as a liquid will be a vapor. But in this mixture region, how do we know what percentage or how much of our initial liquid is actually a gas or a vapor? And that's where the lever rule comes in. Here's the lever rule just summarized here over here on the right, which says that the length of 1, 2, so 1, 2 is just the distance between the saturated liquid line and our initial or total mole fraction. So if I just take that distance and I can measure it, if this is a plot, I might measure it with a ruler. That's the length of 1, 2. Length 2, 3 is this opposite distance, the distance from the initial or overall mole fraction to the saturated vapor line. That's length 2, 3. That is equal to the ratio of the vapor to the liquid. So it's lever rule is just handy because if I can figure out what temperature I'm at and figure out what my initial concentration or mole fraction was and read up to here, I can just measure those distances and that will tell me the relative amounts. What fraction of my liquid has actually boiled off into the vapor phase, because I can find out what's the ratio of the amount of vapor to the amount of liquid. And that's the utility of the lever rule. And so just to summarize, We've had all these different plots here, and all these plots are designed is to help us understand the relationship between the mole fractions or concentrations for a binary or two-component system. And we want to be able to understand this because if we are designing a separations process, we need to know what's the mole fraction of a particular component in one of the streams, in the liquid stream or in the vapor stream. And so we have to utilize these type of plots to help us design and understand these separations processes.